I think we can start now. Hello, everybody. I'm Fang Fang. I'm a lecturer at the Victoria University of Wellington. I will chair this seminar. So Yi now usually chair this talk, but he got some family issue today, so I will be here. Welcome all of you, and we will have Sue from RMIT, from Australia. Will give the talk today. Actually, Sue is a friend from me, and actually, he's a very important person in my supervision team when I was doing my PhD. Um, he worked on quite a different topic. Originally, I learned a lot of scheduling kind of knowledge from him, and also different things. And he now like in the business school. Today the talk will focus on evolutionary machine learning in business optimization. Let's say if you have any question, you can type your question, or at the end you can ask directly. I will record the meeting and can share to all of you in later. I think I should stop here and so you can start.
Thank you, Fong Fong. Let me make it full screen. Is it visible to you? Full screen?
Yeah.
Okay. Good evenings, afternoon, mornings, everyone. So depend on where you are. It's a great pleasure to give a talk in this group, and it's good to see a number of familiar names here as well. Thank you, Email and Fong Fong have organized this talk. As you've seen in the emails, this is about evolution machine learning in business optimization. I'm going to talk a lot about combinatorial optimization because this is one of my main focus. But the whole idea is to see the values of how EML can be useful in business optimization. So this is the agenda of my talk. I just very briefly talk about business optimization problems, the optimization approach. We have seen a lot of experts here, so I'm not going to spend too much time there. I'm going to briefly talk about machine learning's application in business optimization. Then I'm going to narrow it down to evolution machine learning for business optimization. I talk about the case studies that we have explored in the last several years. And I can wrap up this talk with some my thought about recent opportunities and the challenges we may face. So some optimizations, as we know, the current optimization we're looking at is how to select the best decisions, how to select the best combination of things, to optimize certain objective interests. So it's the optimization problems can have many form, many shape, and that is where we do a lot of research on. And when I give this talk to kind of business groups, then usually I have to have these slides when I need to narrow it down to what kind of optimization problem I'm talking about, because optimization can mean very different things depend on the context. So I try to describe it in the context that in which we usually work with is the optimization problem in which we're able to solve using computers. So it's going to be a mathematical formulations. It can be a simulation models. If you're a bit more advanced, you look at the digital twins. This can be data-driven as well. And to there's a number of factors in there that impact how we define optimization problems, including input data, distant variables, constraints, and objective function. Before I go any further, I would like to reflect a bit on the methodologies in which we adopt to deal with practical optimization problems. This is a diagram which I adopt from all the way from 1974. It's very old paper, but very, very good papers. We look at how we approach the real-world optimization problems. We look at the realities, problem situation. We try to conceptualize it. We try to build conceptual models. And when things become clear, we're able to have agreement with our stakeholders. We start with the modeling steps. and it's in which we try to apply different scientific models. Some of the simulations can be some mathematical models, linear programs, for examples. And we try to work our way to deliver a solution or the optimal solution if we want optimal solution. And if we have sometimes we need to go back and try to see where the solution actually is aligned with our conceptual models. And if everything's work well, then we got implement it and see how it's worked in the real world situations. And of course, in there, you're going to see different errors back and forth, try to see the feedback and try to review the models, make sure that we solve the right problems and we're able to get the solution we want. Uh, Another way to look at the methodologies is to look at how we approach optimization problem is also look at the algorithms as perspective, which we actually are doing a lot in this space. I think each of us here, we probably focus on one or two of number of optimizations methods uh, in our research. So we can look at on ways from heuristics to a bit more mathematical approach, to a bit more meta-heuristics, a more empirical approach to solve optimization problems. But still, when we do more and more with optimization, we recognize that there's a lot of bottlenecks happening. So when we're going ahead and try to work our way to achieve, to try to obtain the optimal solution. Some modelings, there's a lot of things that we have to do with modelings, and usually it requires very deep domain knowledge and holistic approach to make sure that we model the right problems. We understand problem well. Sometimes we need to leverage analytics and data analysis in order to give us the best inputs. If it's come with experience, we may have to work our way and try to choose the best modeling techniques, which because it may impact the way we solve the problem as well. And we have to do a lot of experiments, and which require a lot of time budget. We have to formulate hypotheses to test how our algorithm may work. And the more exciting part is model solving. We have models, we have a problem, we try to solve it. And there's so many things that we're doing here. And I believe that most of us here publish a lot of papers within this space. So it's about design solution methods, develop algorithms, run and validate results. And the rest is depend on whether you're gonna actually do research or you actually deliver the solution to your stakeholders. You may want to look at how you interpret the insights. You need to see what we consider as optimal solution, what may impact optimal solution. And we're going to see different kind of alternatives. Like when we have multiple objectives, we want to look at different set of solution. As I mentioned, there's many optimization algorithms ranging from mathematical programming, constraint programming to meta-heuristics, depend on what we like, and also it's depend on the problems. Then we're going to pick one or one of them, or sometimes we can look at a combination of those algorithms and try to find what is the best way to leverage those things to find the good solution in limited running time. But in these areas, we all recognize that there's so many challenges when it's come to optimization problems. So the first kind of challenge which I see is challenging is the distribution variables. So examples where when we solve combinatorial optimization problems, there's a lot of distribution variables. Sometimes the binary, sometimes sometimes the integers variables that we try to optimize. Which if when it's come to mathematical approach, is become quite challenging. And for some meta-heuristics is give us some way to solve the problem, but still a lot of challenges that we may face in order to keep up and provide the optimal solution or near optimal solutions across different problems. Uncertainties is another type of challenge that we face and is very practical issues that we need to consider when we design our optimization algorithms. Uncertainties can come from different types of sources. For example, if you look at stochastic demand, if you look at the production schedulings, if you work in this like job scheduling like me and Fong, then we're gonna see things like machine breakdowns. If you're working in healthcare, if you're working in like a building management, disaster situations, then you have emergency evacuation in which there are a lot of uncertainties that we need to consider. Transportation, traffic control is also another areas in which we have to kind of handle those uncertainties. Sometimes the problem itself is changing, not just because there's some uncertainties, random factors, but also because it's very highly constrained. For example, we work on problems like timetabling, rosterings, and some of the machine learning related problems. There can be quite a lot of constraint in which we need to accommodate. We tried our solution cannot be feasible if cannot address all the constraints. Luckily, you have a lot of tools that are out there in order to help us some kind of relax or even to handle those constraints. Meta heuristics is the area in which I think most of us in here in this space I've been working on. We like meta heuristic solution in because it's able to quite easily to and quite flexible to modify and to solve different kind of problems. And there are different group of meta heuristic out there, genetic algorithms, swarm intelligence, and colonies, and recently there are a couple of more algorithms being developed. And if you look at these broader space, if you look at business space in which organization now they collect a lot more data, they have big data platform in place. They're able to see a lot of data from different sources. They're able to monitor their operations a lot better than before. And that's give them both challenge and opportunity as well. So, for example, opportunities come when you have a lot of data is you're able to make personalized offerings because you're able to understand your customer behaviors, you understand their sentiments. Because with a lot of data, you should be able to make more accurate demand because you're able to connect different factors, different data sources together. You're able to get real-time insights. And all of those things put together is give business a lot of opportunities to work their ways to develop better operational models, to build new business models, and and help them address the needs of the customers a lot better than before. Sorry. Now I move to the part a bit more scenario to the part that we're looking for. So some machine learning for combinatorial optimization. It's not new, but there's a growing interest in these areas in decades. And we have been working in this space for a very long time, but I think in the last 5-7 years, then a lot of more different machine learning techniques have been applied in this space. I'm talking about combinatorial optimization rather than business optimization in here, but most of the combinatorial optimization here I'm talking about is I try to put it in the business context. And be honest, most of the problems I face in the business settings is very much related to combinatorial optimization, job scheduling, timetabling, or production scheduling. They all can be framed as combinatorial optimization problems. And there's a very similar review paper from Yoshi Benjo's machine learning for combinatorial optimization. Have kind of structure and classify different way in which machine learning can be used to help with optimization process. This can be end-to-end learning in which you look at the problem definition, look at the input of the problems, and you try to use machine learning to try to generate the solution directly. So that is a way that we adopt quite a lot in the past as well. Then going to be the learning, the approach for to learning to configure optimization algorithms in which you have a problem. You try to fit into machine learning and try to use machine learning to help to determine what kind of decision within the optimization algorithms that we should pick in order to solve the problems effectively. And the last group is also more challenging group is now we have the problem definition. We try to embed it in we have the machine learning embedding within the optimization algorithms in which it can interact, receive the input from the problems, and also interact with the search status, the search historical status, and try to optimize the optimization on the spot. So we have seen quite a lot of things in here, but this slide. In this slide, I try to capture my view about what is the best way we can leverage AIs and or evolutionary machine learning in order to tackle business optimization problems. I look at the traditional way. When I talk about traditional way, this can be the way that we're looking at how to solve optimization problem probably 2 decades ago, in which we look at a real problem, we try to do modelings, we try to develop solution methods, and if it's working, we try to apply. And in the past, the bottlenecks is between we as researchers and the models we have, and we try to develop solution methods. That process back and forth can take easily several years. And because I came from industrial and system engineering background, so I like to look at the whole thing at the system and see if it the bottlenecks. I try to relax the bottlenecks, probably see it to somewhere else in which it's easier to handle. And for me, I try to frame it up as I try to let's see how AIs and evolution machine learning can be used in order to uh, help us kind of solve the bottlenecks issues for the picture on the left. And the way I'm looking at this is instead of the humans or the researchers to work with the models and try to come up with different solution methods, why don't we give it the design of the solution method, the heuristic algorithms to the AI or evolutionary computation methods to work with? And my focus is to work on, to build a framework, to build a system in which these evolutionary computation AI can work with the models back and forth, receive feedback, and try to come up with a solution method. It can be in the form of heuristic, heuristics, or it can be one of the three approaches that I mentioned in previous slides. So shifting the bottlenecks that we face to the machines, then I hope that that process can speed up. And when when AI is able to identify a solution method, an approach that is happy with, then they can send to the human researcher in which we can modify, we can check and see whether it's appropriate. And we also can suggest how the algorithms can be further explore the solutions methods or the heuristic space. And if we all happy, then we go back and apply. So moving the bottlenecks to that we faced earlier to the machine, we hope that it's able to speed up the way we develop the solution methods in general. So I'm looking at for demonstration. I'm looking at the case studies. The first one is with production scheduling, which is one of the application that I have investigated probably in the last 10 years. Fong Fong is also an expert in this space. So for production schedulings or a bit more narrow is for job shop schedulings. We interest in determine the best sequence in which the jobs are driving at factories, how they can best schedules to be processed at each machine, given that we have a group of machines with different capacities in the factories. We try to find the best sequence for them to be processed in order to optimize a certain objective interest. In this space, the objective interest is can be the throughput, the max span, which telling us how fast the jobs or the products been moving in our factories. It can be a bit more customers oriented objective, for example, the tidiness. How late are we to deliver the products, the jobs to the customers? So there are different objectives that we can look at. Yeah, sometimes we don't treat customers equally. Sometimes there's customer a bit more favors that we prefer because they're important. They bring us a lot of revenues to the companies. So there, this is where we're going to put weight to each jobs depend on which customers are ordering it. So there are different aspects, different objectives that we can formulate. This kind of problem is very interesting because first, it's challenging. Is the very, very typical combinatorial optimization problems. Second, they have different practical application, real-world applications. And third, as mentioned, there are different objectives that we need to address. So tick on the box is one of the problems that I'm very interested working on. And for the computer science and operational research communities, is one of the problem. If they have any new methods, this is something that they need to try on. So I've been working on different evolutionary machine learning frameworks for learning scheduling heuristics for these kind of problems. And usually the framework can be in different form, but in general, it's going to look something like this diagram. So you have a production scheduling problems. You need to figure out, you understand the problem, and you need to figure out in what way, in how can we come up with a heuristic that we can solve the problems. The heuristics in here is quite abstract terms because it can be in different forms. The one that I'm working a lot in the past is what we call priority dispatching rules, in which we try to schedule the job based by assigning the jobs a priorities. And how can we assign the priorities? There are different ways, and the way we can, one of the easy way to do it is to have mathematical formulas, taking all the inputs of the jobs and operations, and try to calculate the priorities for that corresponding jobs. And I look at the heuristics and try to break it down into smaller components and try to see which one we need to fix and which one we need to improve, we need to optimize. And when I identify which one I want to optimize, or in this case, which one I can evolve, then I'm going to see what can be input to that components. If you're working in genetic programming, then you need to determine what is the attributes, what is the terminals that we can use to, and what kind of functions that we use to connect all of those attributes. So that together become the representation. You need to come up with some kind of representations of the components that which you try to evolve. If you work, if you're new to this space, sometimes you think that, okay, you have meta algorithms for the heuristics, and you try to evolve everything in there, which is possible. But for my experience is that I try to look at that and say which one is already good and there's no point to change, then I'm going to fix it, which helped me to narrow down the search space and help me make a more compact representation of the heuristics. So when I have I have all the components, all the ingredients that I need to build heuristics, then I can fit it into these evolutionary process in there, in which they have finite evaluation, in which they have the reduction genetic operations. And usually they're going to have some form of evaluation model. It can be training testing data. It helps me kind of checking whether it's the heuristic I create during the evolution process, whether it is good or not. And sometimes we also have the post-processing process. So it's when we get the best heuristic out of the evolutionary process. And sometimes it's quite big, we can understand, or sometimes we just want to further fine-tuning it. So we may have some kind of post-processing step as well. So the first, to make it easy, the first thing I try to do is try to solve the static job shop scheduling problem. The table on the right is going to be a simple examples of the static job scheduling problems. You have the route with the sequence or the machine in which the job needs to go through. They have release times when the job going to be ready, and the duration in which the job need to spend at each machine. They have WJs in there, is the weight. As I mentioned, high number is going to be considered more important. DJs is going to be the due dates that we consider. The smaller due date means that the job need to deliver very soon. All right. So usually is when you solve the job scheduling problem, you actually try to build a schedule similar to the Gantt chart I show on the bottoms. And with this Gantt chart, you can if you have interactive Gantt chart, you can move things around and you see, so okay, I want to do the job first before the others. You're gonna see there are different schedules that you can generate. And the number of solutions here is gonna be huge. Okay. Of course, you can solve this problem using genetic algorithms, and is a lot of work has been done there. You can even using mixed integer linear programming to solve this kind of problems. But in here, I mainly focus on the inspection rules, or high level, you can also call it construction heuristics. So I'm going to focus on, okay, it's the queue in front of the machine. At any point in time, if you look at the factory settings, then in each machine, there's going to be a queue of jobs, the jobs that be ready to be processed on the machine, but the decision that you need to make now is which one you need to process next. So for that decision, then to make that decision, then we need to come up with some kind of inspection rules. And the inspection rules basically tell, okay, we have three jobs, which job from 1 to 3 I need to process first. And depend on how I decide, it's gonna impact the qualities of my schedule. So there's a lot of existing rules. It has come from very simple rules into very complex rules. For example, minimum slack here is basically just to look at the time from now until the deadlines. So if it's very close, we have to process that job first. Sometimes we look at our ratio, let's say between the wait and processing time. So the job that be more urgent, and if we can process as quickly as possible, we go with that one first. But sometimes you combine a lot of things together. For example, the appearance tardiness cost, ATCs. You combine both of those all those components together. So it can be very simple. It can be very complex. So my question is that we already know the form. This is the mathematical functions with input is the data for each jobs, and also sometimes the information about the systems that we're looking at. So the question is it possible to design better priority functions rather than the trees here? The fact is that they have about 30 very popular dispatching rules in the literatures. But do we have only 30s, or we can do more? We can have more, or we can have much better one. So that's my questions. So I prepare. So with that in mind, I try to bring all of them together, as I mentioned in previous slides, to build a representation of these things. I need to have the attribute. I need to have the functions. So the function can be something symbols. You can arithmetic operators, plus minus divisions, multiplications, min max, log, whatever. For the terminal, this can be on these attributes of the jobs and machines. So put them together. Okay, how can we represent it in computers? Then turn out it's quite easy. You can use a tree format in a tree structure to represent such equation. It can be the pictures here represent two very simple examples with that of an equation. And if we work in evolutionary computation, then we need to say that, okay, we have a lot of individual. Each individual is going to be one mathematical formulas. Then for the next, we can able to evaluate them. Yes, we applied it to different training instances. We try to use them to prioritize different set of jobs, and we see how good they are by evaluating the schedule. But the next step is to, okay, so now I know which one is good, how can I progress? So this is where we need genetic operators. It can be subtree crossovers, can be subtree mutation. I'm not going to I'm going to go too deep into this one because of the time limit. But subtree crossover and subtree mutation, they are very simple approach that can easily apply if we represent our individuals in a tree structure. And it's worked very well in most of our papers. So apply these two, we're able to, from the parents' population, we're able to generate new offsprings, new child programs for the next step. So we can repeat this step from time to time in order to improve the qualities of our heuristics. All right. I'm going to move a little forward to look at the results. This is some work that's been done a very long time ago. So this is very much a first attempt to apply the genetic programmings, the heuristic created by genetic programmings into very traditional static instances of shop. We compare that with different inspection rule. We compare that with some meta heuristic as well, and we see that with a very straightforward way to construct a heuristics, just create the priority rules to assign priority to each job. We're able to already achieve very good performance already. So that's very encouraging. But we move, this is a bit more recent work that we've been doing. So instead of, okay, we just share it, we just have the inspection rule, try to construct a solution directly. Can we build something that we can, in a later stage, we can improve it without making too much simplification, modification? So that is where I'm thinking, okay, when we have the problem formulation, usually what we're doing is that we have the problem, we try to formulate the problem, we fit them into the solver, we want to get a solution. That's what we want. But usually this approach can only work for a small instances, and sometimes it may take some time to produce acceptable solution for medium and large problems. But this is basically what we prefer to do, because in the business settings, they're interested in the problem formulation, define the problems, but they don't have a lot of knowledge. There are a lot of technical knowledge in order to come up with the fancy algorithms that we develop and make it work from time to time and maintain it. So formulation is something they can work on. Problem description is something that they can work on. So whether we still can look at this diagram, every tricky things, we can use machine AI, whatever, to solve it. That would be the best outcome. So what have we done in the past is that we come up with a genetic-based constraint programming in which we apply very much the same trick we have earlier, which I tried to develop the priority rules, but instead of use that directly to sequence the jobs, what we're doing is that we use that to determine the order in which the variables within constraint programming is going to be exploring. So if we only try to find a feasible solution, it's work very much similar to the way we applied earlier. But if we, after determine the feasible solution, CB allow us to, with the search algorithms, it allow us to search for optimal solution. So that's quite a good combination. And the goal in here about priority function is not to find the first best to directly spit out solution, but spit out something that work well with the CB search algorithms. And we are running some experiments with this new combination, and the results is quite encouraging. So if you look at CBs, then it's about branching different variables and try to find the best combination of variables values. So the number of branches that CBs work, you need to achieve to identify the optimal solution, to prove optimal solution. is on the first graph on the left, is in here. And this is what we try to measure because it shows the effort that CP need to spend. And with the red bar is the default settings of our CP solver, and the green one is the one in which the evolved heuristic or priority rules used within the process. And we see that the number of branches, the number of computational effort have been reduced significantly. And depend on what kind of problems we're looking at, we're able to achieve quite a lot of performance speed up. And if we look at the solution qualities, we're able to achieve some improvement in solution quality as well. For small problems or easy problem, probably we don't see much in terms of solution qualities improvement. But for a challenging problem, for example, total weighted tardiness, we're able to see quite a massive improvements in this space. If we give the solver kind of fixed time, which time to work with. In some case, we're able to prove optimalities a bit for a lot more problems compared to the default settings of the CP solver as well. We also compare, okay, we use GBs, but we can also apply other machine learning techniques to do the same things. And so we also compare GB with other methods, for example, some multi-layer perceptron, small factor machines, or we can look at the supervised version of genetic programming as well. And we see it's quite a good performance of GBs across different aspects. Some for example, Cmax stand for max span or throughput. GB still perform very well. For this Tmax maximum tardiness, it still performs quite competitive against other machine learning methods. Slightly worse when the number of methods, the size of the instance getting bigger. It's mostly because the combination in these combinations, the machine supervised learning machine method have been trained on much larger training set with a different size. So that gives them a bit more advantage. But usually they're quite compatible. We also see whether we can go beyond job scheduling. So we applied to other problems. For example, this case, we look at our resource constraint job scheduling, which is more like a combination of job schedulings and project scheduling in which you have renewable constraint as well. So it's slightly challenging, and we have to solve, we need to make schedule decision to achieve our objective, but we also need to look at our constraint on the resources, the kind of universal resources as well. And the results also, again, is very encouraging for this approach. We perform well, we're able to improve the objective values. For this problem, we also have a chance to compare with across how our method perform across different GBs, setting different implementation, and see that with appropriate choice of implementation, we're able to achieve quite good objective values. We also compare with different objective algorithms, for example, ACOs or math heuristics for like column generation plus ACOs, for examples. And we see that this kind of our proposed methods can work well, especially when the problem size increase. I'm going to quickly go through these dynamic part as well, and then hopefully I have about 5-7 minutes to wrap up. So this is previously I'm talking about static problems, but and now the best application of our proposed method is for dynamic job scheduling problems. And as mentioned in the business settings now is where they have more way to collect data, they have LT device sensors in order to get a real-time situation. So dynamics job scheduling is no longer what we assume in the past, but it actually is something that is working right now. And this is now it's only depend on whether we want to be that reactive in a way for making decisions. And in this space, again, we are able to achieve very good performance, even when we're working across of many conflicting objectives. This is one of the work we done about 10 years back, when we compare our evolved heuristic against a group of benchmark heuristic developed by human researchers. And we see that there's a lot of space in a lot of solution in the heuristic space in which human research had never been explored. And using our approach, we're able to explore all of those areas, and that allow us to understand the trade-off in which we're able to achieve, rather than just simply follows all of traditional heuristics proposed in the literature. In this space, we also thinking of we are thinking of another problem in which set down the one who apply this solution, they need to be comfortable. They need to accept the way in which our heuristics been made to solve the problems. So we want to make sure that the decision makers have a voice during the process in which the heuristic design. So we come up with what we call people-centric evolutionary systems, in which instead of following the traditional evolutionary process, we create a feedback loop in which we're able to monitor what solution have been created, and we have the interactive features which allow the decision makers or the users to interact with the process and give the process what they prefer. We hope that throughout this process, we're able to gain a bit more acceptance of the heuristic solution at the end, the one that's been spit out by our systems. This is just a snapshot of the visualization tool we built within that people-centric evolutionary systems, which allow us to monitor what solution have been created. Each dot in here represent one individuals or group individuals. If you see a bigger dot here, which means that there are a lot more individuals being generated within that area. And the color represent how good they are, how good they are, or how recent that individuals have been created by our systems. So through this system, we're able to see how our algorithms converge on how diversified they are they able to cope with, able to overcome or escape from local optima. So and this actually is in our system, the users can actually interact with this cap diagram and try to see, okay, which areas, in what areas, what kind of heuristic that we have created, and they can look at that, and then they can see whether that is the solution they prefer that align with their preference, and that's going to be the input for the system to evolve further. And our experiments also show that the system works very well, and with a proper control, it's also able to reduce the size of the heuristics, which make it a bit more interpretable. And well, of course, it is smaller when applied, it's a bit more computational efficient. I think I'm going to use 2 minutes to wrap up. Bit more recently, there are a lot of advances in this space. A lot thanks to the work of Feng and email. And to be honest, evaluating the heuristics sometimes it can be quite expensive. So using surrogate models can be quite helpful. It's going to help us to speed up the evolution process and sometimes help us converge to a better solution much faster. We have different tasks that we need to solve with a group of heuristics. So multitask learning becomes something very helpful. And we have making some progress in this space as well. Sometimes we have different part of this, and we have different decisions that we need to combine together to form a comprehensive and feasible solution. So cooperative convolution becomes something very handy, help us to break down the solution space with efficient way to put them together. We're able to solve the problems a lot more efficient. And of course, we look at a lot of new way in which we can generate new upstream rather than random generated operators like subtree crossover and subtree mutation. Then there's some other way for us to generate better individuals. For example, look at the importance of each subtrace, each terminals, doing a more effective feature selection. And recently, some people also leveraging large language models in this space in order to come up with directly generate heuristics, but you still leveraging evolutionary computation to generate new heuristic over time. Okay, to wrap up, just a few thoughts about the future research directions. This is the slide that I created quite about 2 years ago, but I think it's still relevant now. So the first one is, can we use AI to replace the support optimization expert to design an efficient way to solve reward optimization problem efficiently? I think we do it partially now, and some of them work, some did not work. There's a lot of things that we need to learn now. So but ideally, the way I'm looking at it is I look at it from the user perspective. So I want decision makers, users, analysts to focus a lot more on the real problems, try to formulate the correct problems, and don't need to worry too much about how to solve them. And solving them can be improved over time if we apply appropriate learning methods or evolutionary approach. Also interested to see how we can transfer the knowledge that we learn from solving one optimization problems to another or other related optimization problems. I think this one we can take it about because we have a lot of work on transfer learnings and multitask learnings. Fang Fang is an expert in this space. Can we learn multiple optimization tasks at the same time? That's for multitask learning. And can we freely formulate optimization problem and freely allow AI and machine learning to discover how to solve them? It's quite similar to the first one, but a little bit more, give a bit more freedom in the way we combine with different methods. And the last two is a bit more of a way I want to including human in the loops. And it's now it's quite aligned with the responsible AI frameworks that people try to develop all around the world. So I try to see is whether AI machine learning can learn how to represent a solution to us in a friendly and interactive way. And can human and AI system communicate and co-design solution for complex optimization tasks? So it's just some question for us to think. I don't have a definite answer for all of those. In some of those, I'm making some progress, but still a lot of things to explore. Thank you very much.
Thanks, Sue, for your great talk. Let's open to the questions. Anyone have any question? You can type your question or ask directly. We have several questions there. Sue, can you see the question?
Yeah, I can see the questions. I probably go from top to bottoms. Is there any suggestion for designing the simulations so that the compare methods have larger performance gap? Okay. I think this is a bit more about theoretical question because we only try to prove that our method's working better in one way or another. So it's a bigger the performance gap actually is helpful. I think the short answer is yes, we should be able to do something like that. I think if we look it up from publication perspective, then the no question is that whether it is advisable to develop the problems from our end or not. Things are from my end is that because at least in the last 5-6 years, I'm working more with practical problems. So I try to see the challenge from the practical viewpoint. And always as when you incorporate more and more practical constraints, more practical requirements, it's automatically become more challenging. But I think in combinatorial optimization problems, the challenge is that there is not it's not a smooth. It's not smooth. You cannot incrementally increase the complexities. Sometimes it just jump. So this can be very easy problem there. You introduce a new constraint, it jump up to whole new levels of difficulties. So yes, you can. But yeah, I'm probably it's not usually the way I look at it. Uh, Hopefully that address your problems, your questions. Sorry. And the models are what your experience in explaining GB solution to customers. Very good question. I try a few times. Even though what we usually think the priority function, for example, is an easy way to explain, and usually we can come up with something very small. It not necessarily becomes something easy for the customers because first we don't know who they are, what's their background, and yeah, usually they look at the equation. Sometimes they freak out, they panic, and they don't want to look at it anymore. But some of the trick I'm apply in the past is that even what I'm developing is a priority function, but I try to explain it as kind of as design rules. If this will happen, this will happen, and usually they're quite comfortable with that rather than give them an equation or whatever or program. Uh, okay, next one is what about the nature of the solution of AI? Is it optimal or not? I think is a very, very broad, high-level questions. I think I need a bit more context here. I think from this, what I just want to say is that AI not going to deliver everything. It helps for certain things. For example, machine learning is can help to learn from experience, and if we're able to leverage that experience well, we're able to learn something helpful, then it's helpful for the things that we want to do. But definitely, I don't think it's can able to solve all the problems. If AI is machine learning, if we apply it well, it's combined with the tools, the very effective tool, very effective and proven tools. I think that is the thing that I'm hope that work. AI alone, without combination with any other tools, is going to be tricky. Things I didn't see. Could be seen. Could it be seen as enhancement of other methods? I can put it this way, and I think most of my work have been surrounding that ideas. I have something that work, something that people comfortable with, but it's required a lot of expertise. It's required of a lot of time to build it. Then this is where things AI become very handy. It speed up the process. Sometimes it can help to expand process. For example, if you look at if I move back a few slides here, uh, all right. If I look at these pictures and I see the bottlenecks, if I try to shift here of finding solution methods, if we're able to successfully solve that part, then the next bottleneck I'm thinking is about modelings or about applying. And now we have a number of people working together and try to see how AI can help with the modeling part. So I think the best part is that I go in around the factories. I can see the situation. I can describe the problems. I can note down all of the things I think important. And I write down as a few paragraphs. And when I want to send it to the thing that ChatGPT and ChatGPT can help me formulate the problems, CPE problems or mid problems. And we can put that into next steps. So that's another way to in which AI can further enhance this process. Stephen also have a question about how the messages allies in the schemas and the slides of genetic-based concept programming should be updated in order to handle dynamics job scheduling. Very good questions. Short answer is that it can be. I think it's about how we want to, things now, one step back is about how we want to handle the dynamic situation. The one that we want to handle earlier, that we used to, we apply to handle dynamic situation is reactive scheduling. At any point in time, we make situation, we look at the local information, we look at the information we have that time, and we try to make decisions. But there are other methodology methods kind of approach as well. For example, proactive schedulings. We can every time you schedule a job, you have some uncertainties. We have machine breakdown. For example, you do the rescheduling. So when you rescheduling, you can apply the same genetic-based constraint programming again. If you to reschedule the job that you schedule earlier, but have not yet been processed, combined with the new jobs. So that's another way to look at that. And in that sense, then people also want to look at not just the objective, but also the stabilities of the schedule. So yeah, you may want to dig a bit deeper into what is needed, depend on what approach you are adopting. All right. Can GCP solve large job scheduling problem instances, for example, thousands of jobs and 10 machines? It's gonna be tricky because CBs is gonna consume a lot of memory as well. So it's depend on situation. But even I think if it 10 jobs and 10 machines, if I use genetic algorithms to solve that kind of instance, for example, I'm looking at 10,000 variables there, the dimension of 10,000. So it's going to be challenging for any algorithms, not just the GCP. But to be practical, if I have that kind of problems, I try to find a way to relax or decompose it somehow. I'm not going to solve all of them in one shot.
When people are thinking about question, I have one question I want to ask. So you also mentioned large language model when I attend conference. A lot of people talk about that. How do you have any idea or have you seen any good publication about this in this domain?
I think there's some some promising one in the literatures. But I think now is at a state more or less similar to using large language model as the generators of heuristics that we used to do using genetic programming. In genetic programming, we need to define everything very carefully and we have a very strict structure, make sure that everything is good, and then try to put them together and try to explore that space. For large language models, is rely a lot on is prior knowledge, try to put things together. There are some clever use of prompting in order to make it work. But the outcome is still quite similar to what we did earlier, I would say. Not going to be a massive difference. So the question is that whether we want to use that for the next step or we can combine that with what we have now and how, right? So and for me, that is still quite open space. But well, one of the things I'm thinking right now is I'm trying to do some experiments at the moment. Is you remember in the past functions we tried to come up with a big set of features
Yeah.
to do feature selection, but not very successful. I think we might move up to 20, 30, but no more than that.
Mm.
But you can use a large language model to check about hundreds of thousands of features by just looking at the what scheduling literatures having, you can look at 100 papers from literatures. Each one talk a little bit about what features is maybe helpful for solving for certain problems. You can bring all of them, ask that large language model to check those features for you, and combining with your existing framework is just another way to make it work. For me, that's a very easy way to do it. And yeah, you can further proven that your shared programming work, but you don't need to worry about the features part as well. Because one of the earliest, one of my the challenge I seeing is that it's hard to create features for new problems or any kind of variants of scheduling problems. But all the knowledge has been staying here and there in the papers here and there. It's just about how you combine them, and large language model will give you a clever way to combine them. Sometimes it may not work, but sometimes it may work. But there is where your feature selection may work. You're able to filter out which one that useful for the specific problems that you want to work with.
I think it's interesting. Yeah. We have one more question from the chat.
Yeah. Is this model able to apply on emergencies department for scheduling to automate resource utilization and reduce waiting time? Thanks. I'm not sure because I have not looked at that emergency department workforce scheduling problems, so I'm not quite sure what decision that we try to figure out, which we try to optimize. But the idea is there. I think, yeah, I'm not quite sure, to be honest, because I need to look at the problems. Stefanos, may you explain again how the users can interact with the evolutionary process? I think I can move a few slides up. Oh. Yep. All right. So I think the whole exercise I try to do here is that instead of having the evolutionary process go through hundred of generation as a black box, I try to make it a bit more transparent. And my way of making it more transparent is I try to map out all the individuals generated across generation. I try to map, and the map is I use is in the form of a diagram of a network. And each dot in here represent an individuals or a group of individuals. If they're similar, they're gonna be just represented as one dot. And each dot in here, I'm gonna use so the one that close to each other, they're gonna have similar behavior. And how I measure behavior, we have different ways to measure behavior. We in this case, in a lot of our work, we use phenotypes as the proxies for the behavior. And we use that as a vector. So with the vectors, we have two different vectors represent two individuals having their behavior. And if they are similar, they have similar, we mean that they very close to zero distance. Then they're similar, right? So they're going to be close to each other on this network. So that network can tell us where in the suspect we have explored. And if I move to the next slide in here, you're gonna see that for example, in generation zeros, things can be all over the place, here and there, all over the place. But go through generation, go moving ahead there, you're gonna see that the evolutionary, for example, generative programming, they're gonna start to converge. They try to they try to do more exploitation rather than exploitation, rather than exploration. Yeah, at some point it converge and converge more and more. So this is the map that we try to create. And we're actually building interface so that the users can stop the generation at any time, and they can click on the dot here, and you're able to see the formulas, the function that represent that dot, and the users can look at that and see whether it's aligned with the usual way in which they kind of making decision. And if they can check different nodes, and if they have a node in which they can say that this is quite similar to what I'm doing, I want to enhance it, so they can choose a few dots in which they want to enhance, and that's going to be the input directly, and they give the input directly to the finish function, which give GB a bit more pressure to explore further in that direction. It's a bit quite a long explanation, but hopefully you got what I mean.
Thanks. Any questions? Final question? We got one more question.
How to solve the generalization problems of AI-assisted optimization algorithms on large scale. AI-assisted automation. Um, mm, no, I think that I'm not quite sure I understand the question that clear. Um, so, so let's say I try to break it like AI assisted optimization algorithms. So they're going to be AI assisted and optimization algorithms. So the optimization algorithms, it can be meta heuristics. It can be conventional meta heuristics. So AI assisted can help with any of those groups. It just depends on how you want to leverage the outcome from AI to help with the meta heuristics. Certain combination may work. Certain combination can be quite silly. Those are, I don't think I have a question for this, but it depends. It depends on the problems. It depends on how we leverage the outcome of AI. For example, I think in the past, sometimes we're just doing something very simple. We use static programming to generate our initial solution, and we just feed them to a hybrid algorithm, GA plus local search, and it's immediately speed up the process. So for me, that's the easy way to do it. But some people are also thinking, okay, I'm going to leverage that, and then I use that to come up with a complex probability distribution of solution and fit up into, let's say, ACO. It may work, it may not work. And we also saw something like what I demonstrated earlier with the GCP. Some people also think, okay, whether I can look at the variable orderings from given by the priority functions and try to for each node in which CP can explore, I can apply it. That seemed to be quite good ideas at the beginning, but applying and if every node of CP actually slow down the process quite a lot. So for us, we only apply at the first layer at the root node, and that's it.
All right. I think we can stop now. If you have further question, you can email Sue. Um, and in Melbourne, it's already 8 p.m., right?
Yes.
Thanks, Sue, for giving such an interesting talk. I think we should give you some time to take a rest. Thanks again, and hope to see you in person in the near future. Thanks. Thanks all for coming.
Thank you, everyone.
Thank you. Bye bye.
I'll see you.
See you.